You know, every single chemical reaction, from a roaring fire to the quiet, tiny reactions happening in your own cells, is all about energy changing hands. But here's a thought. What if you need to know the energy of a reaction you can't actually do? Well, today we're going to pull back the curtain on a super clever shortcut chemists use to measure the truly unmeasurable.
No, really, think about it for a sec. Some reactions, like rust forming on a nail, are just painfully slow. Others might be way too dangerous to run in a lab. Maybe they're explosive. Or maybe they just create a huge, messy soup of byproducts you don't want. So, how in the world do scientists get the crucial energy data they need for these things?
On one hand, you've got something like magnesium dropping into acid. It's fast, it fizzes, it gives off heat you can measure, no problem. Perfect. But then you've got rust. It's definitely happening, but you could stare at that nail for your entire life and never be able to measure the heat coming off of it in real time. That is the exact challenge we're going to solve.
Okay, so to even start to solve this puzzle, we need to get one thing straight. There is one single fundamental rule that's in charge of all energy everywhere. Seriously, it's the bedrock for everything we're about to talk about.
This is the big one, the law of conservation of energy. And it's actually pretty simple. It just means you can't make energy out of thin air, and you can't make it disappear either. It's always there. All a chemical reaction is really doing is, well, it's like energy accounting. You're just moving it from one column to another, changing it from chemical energy into heat or light or some other form.
So, since energy is just being moved around, let's look at the two main flavors this comes in during a chemical reaction. Basically, you've got reactions that give off heat, and you've got reactions that soak it up. And I guarantee you've felt this before. An exothermic reaction is one where heat exits. It releases heat, making things feel warm, just like a hand warmer. The opposite is endothermic. It pulls heat into the reaction from its surroundings. That's why those instant cold packs you have to snap feel freezing cold. They're literally sucking the heat out of your skin. Let's break that down just a little bit. In an exothermic reaction, the hot one, the stuff you end up with, the products, actually have less stored energy than what you started with. Why? Because that extra energy was released as heat. Scientists call this energy change enthalpy change, or delta H, and for exothermic reactions, it's a negative number. For endothermic, it's the exact reverse. They absorbed energy from the outside, so the products have more energy, and delta H is positive. But why does this happen at all? Well, it all comes down to the energy stored in chemical bonds. Here's the most important part. Breaking bonds always costs energy. You have to put energy in, kind of like snapping a twig. But forming new bonds always releases energy. So the overall reaction is just a simple balance sheet. Did you get more energy back from making new bonds than you spent breaking the old ones? Boom, it's exothermic. Did it cost you more energy to break the bonds than you got back? Well, that's endothermic. Simple as that. Okay, so we've got the theory down. Reactions involve heat. But how do scientists actually measure it for those reactions they can do in a lab? Let's check out the tool for the job.
Say hello to the calorimeter. Now, it sounds fancy, but the idea is incredibly simple. It's basically just a really, really good thermos. It's an insulated container that's designed to do one job perfectly: trap all the heat from a reaction, so none of it can escape. And using it is just as straightforward. You run your reaction inside, usually in some water. Then you just measure how much that water's temperature changes. A quick calculation later, and bam, you know exactly how much heat the reaction produced or soaked up. It's simple, it's effective, and it's direct.
And this brings us right back to our original problem. A calorimeter is fantastic for a nice, fast, clean reaction. But you can't just stick a rusting nail in one and expect to see the thermometer budge. It's just too slow. So what now?
This is where the genius comes in. When a direct measurement is just not possible, chemists have this incredibly elegant and powerful workaround. It's a fundamental law that lets them calculate the answer without ever having to run the impossible experiment.
It's called Hess's law. And the big idea here is that when it comes to energy change, the path you take is totally irrelevant. All that matters is where you start and where you end up. The total energy change between those 2 points will always be the same. The absolute best way to think about this is like hiking a mountain. Imagine you start at the base and your goal is the summit. Your total change in elevation, let's say it's 3,000 feet, is fixed. It doesn't matter one bit if you took the super steep direct path straight up or the long winding scenic route that goes all the way around the mountain. Your net change is identical. Chemical energy works the exact same way.
So here's how that looks in chemistry terms. Getting from your starting stuff, A and B, directly to your products, C and D, that's our direct route. It has an energy change we'll call delta H1. But if we find another way to get there, an indirect path through other steps, the energy changes for all those little steps will add up to the exact same value as delta H1. It has to.
So, we have all our tools now. We've got the law of conservation, we understand enthalpy, and now we have this amazing shortcut, Hess's law. Let's put it all together and finally solve our original mystery.
Let's use a classic example. Finding the energy change when we form methane, natural gas, from its basic elements, carbon and hydrogen. Trying to do this directly in a lab is a complete nightmare. You get a whole bunch of other stuff, not just methane. So that top path you see, the one we actually want to measure, that's our impossible reaction. But, and here's the trick, while making methane is hard, what's incredibly easy? Burning it. And it's also super easy to burn its starting ingredients, carbon and hydrogen, all by themselves. These are fast, clean reactions that are perfect for a calorimeter. These reactions are indirect scenic route. This energy level diagram is the real aha moment. Look, the path we want to find is that small step down from the top level to the middle level. We can't measure it, but we can measure the huge energy drop from the very top all the way down to the bottom. That's just burning our starting materials. And we can also measure the drop from the middle level down to the bottom. That's just burning the methane itself. So, can you see it? The energy of our impossible path is simply the difference between those two big drops that we can measure. It's just a bit of clever subtraction. And when you do the math, using the real data from those combustion experiments, you find the answer. The enthalpy of formation for methane is negative 75.0 kilojoules per mole. We just did it. We found the energy of an impossible reaction, and we never actually had to perform it. It's a definitive, satisfying answer, all thanks to some clever energy accounting. So why does any of this matter outside of a classroom? Because this is absolutely crucial stuff. This kind of calculation is used to design more powerful rocket fuels. It's used to engineer industrial processes that save millions of dollars in energy costs. It's even used to understand the complex metabolic pathways that are powering your body right now. This is fundamental. And that leaves us with one last thought. We've seen that energy is a constant. It's like a cosmic currency that just gets passed from one form to another, but it's never really lost. Which makes you wonder, doesn't it? If all that energy is already out there just waiting to be transformed, where are we going to find the next great source to power our world?